All right. So, oops, I should have had the slide break here. Oh well. So we'll be here again. A lot of discussion is going to happen around ways to keep our gradients from vanishing, right? That's the vanishing gradient problem, without also causing them to explode, right? So we don't want to have our gradients explode, which causes our weights to ramp off to infinity or our updates to be unstable, okay? So we're going to talk a lot about trying to keep that error signal in a stable region where it's not either vanishing or blowing up. Okay? But AI winter. So the vanishing and exploding gradients problem caused a thing called AI winter, right? So the vanishing gradient meant that you couldn't make networks more than, let's say 3 layers deep, right? If you made a 4 or 5 layer network that's perfectly well defined, right? You can write down the math for the forward and back pass unambiguously and you can build it, but the vanishing gradient problem will mean that the lower layers never get trained, so you're basically only going to have the learning power of the last 3 layers no matter what you do. In the late 80s, people ran up against the limits of what a 3-layer network could achieve, right? They were hitting problems where you just were going to need more capacity than that, but they couldn't train it. And they didn't necessarily understand this problem in these terms at the time, to be fair, right? Another issue that is perhaps discussed less than it should be is the need for big data and big compute, right? So we talked about how high-capacity models need lots of data. In the 80s, they did not have lots of data. But we'll come back to that later. So 2 early sort of techniques that helped get us out of AI winter are convolutional networks and deep belief networks. And for our purposes right now, we're going to look at deep belief networks. So we're going to talk about them briefly. So deep belief networks were a huge, huge deal in 2006. They were introduced by a guy named G.E. Hinton, and he used them to pre-train the network. So he basically figured, what if we had some way to start the bottom 4 and 5 layers of a network, right? So if you kind of picture your network, right? And I'm going to draw these layers not very wide. If you picture your network like this, and you know that after about right here, right, your learning signal will be zeroed out effectively, and that these layers are going to get a very tiny learning signal. He basically had the idea of, what if we had a way to figure out kind of what a good weight init... So basically, what if we could figure out kind of what we wanted our weights to be before we even trained them? What if we could make an educated guess as to what those weights should look like? That way, if we can start out close to the target, right, close to what they need to be, then that tiny, tiny little error signal, that almost zero error signal, might actually work, right? Because they won't need to correct much. And he figured out, if you have a deep network like that, what you probably want these layers to do is feature extraction. You probably want them to respond to patterns in the input and to be performing pattern recognition. Okay? So he figured there is another type of machine called an RBM, a restricted Boltzmann machine, that we have a good training system for. And what it does is it is good at data compression, which is to say it is good at recognizing patterns in input that can be used to reconstruct the input, which is feature extraction, right? It's good at noticing the important parts of data. And so what he did is he trained restricted Boltzmann machines, and they also have a weight matrix in them, so he trained them, and then he yoinked out the weight matrix and used it to initialize these connections. And the theory being, that was probably going to be close to where they needed to be, so that teeny-weensy tiny error signal would probably work. And so the other thing that he did is he stacked them, right? That logic works if you want exactly one more layer here, but what if you wanted to have a 6 or 7 layer network? Well, he just kept stacking them. He would add another RBM and train it to reconstruct the output of the previous one. And that way he could just sort of keep stacking them in layers, and he would use those weights to initialize his network on the theory that the little teeny tiny near zero error signal would work because they'd be close to where they needed to be. And in practice, it turns out this worked, right? So this pretty much kicked off another explosion in interest in AI in 2006 or so, because he unlocked the ability to train much deeper networks that could solve much more interesting problems. Since then, we have found cleverer solutions to the vanishing gradient problem that have allowed us to explore definitions of deep way higher than 8 or 9, right? So he pushed the definition of deep out to 8 or 9 layers, right? And his pre-training scheme is kind of expensive, right? It adds a lot of extra work on top of the training you were already going to do. We have since found ways that can just improve the error backflow so that we don't have to do this, and we have made much, much deeper networks. And now, only 14 years later, which is not, insanely long, we live in an era where deep means like more than 1,000, right? So once he sort of kicked off interest in AI again, we have rapidly pushed out the boundary of what deep is, and that means that we have rapidly pushed out the boundary of what AI can achieve, right? And just to be clear, I'm not going to make you build an RBM yet. Building RBMs is an optional special topic. It might be fun. They're neat. But we don't have to do it if you don't want. I'm not going to teach you directly pre-training unless you ask, because nobody does it anymore, right? That's kind of one of the downsides of living in a fast-moving field, is that even major breakthroughs have a short shelf life, right? And even like 10 years later, nobody cares about pre-training anymore because we have much better solutions to the same problem. So we're not going to discuss the math here because DBNs at this point are more of a history thing. So the other little thing about ending AI winter is the advent of massive internet corpuses, right? So very deep models require a lot of training data, and it wasn't until you had companies like Google and, I want to say Yahoo, probably not Yahoo anymore, but Google and Facebook and Instagram that are slurping up huge, huge amounts of data that you start to see corpuses of text, like for Wikipedia, for example, or spoken word for LibriVox, or images, right, from Instagram or Facebook, right, that you start to see corpuses of just raw, random, broad topic, human speech, or human image, or human text that you could train that you had enough data to train these deep models on, right? So that's the other sort of lesser thing. And again, that's kind of why I sort of like to hit on the idea that some of these amazing breakthroughs really kind of depend on you being Google, right? And that's one of the reasons is you really kind of needed, in order to train something like GPT-3, you needed somebody to produce a Wikipedia scale or Twitter scale text corpus, right? And that just didn't exist in like 1989 or 1995, right? That just wasn't there, right? In 1995, you might have thought a lot of text, quote unquote, was like, I don't know, a newspaper, right? And by modern standards, no, right? All the text in like a newspaper or a novel or a dictionary is not anywhere remotely in the same league as the size of like a Wikipedia text corpus or like an all Twitter text corpus. And that's really the thing you need to train a massive language model. And again, if you're talking about training like a hojillion parameter model on terabytes of text, you need very powerful compute, right? You need some big iron compute. You need rooms full of GPUs compute. So while sort of deep belief nets were the major breakthrough by G.E. Hinton that ended AI winter, GPU Excel and like huge text corpuses like Wikipedia are also sort of necessary building blocks, like necessary dominoes that also had to fall to get us to the modern era of amazing AI. Okay.